This is the first video in our series on quantum mechanics. It is meant to provide an overview for the remainder of the lecture videos on quantum mechanics. By the end of this series of lecture videos, you should be able to, given a wavelength of light, determine the frequency, and vice versa, list the 7 areas of the electromagnetic spectrum in order from high to low frequencies, describe what is meant by the wave-particle duality of light, given the energy of a photon, determine the frequency and/or wavelength, or vice versa, given a starting and ending orbital, predict the amount of energy absorbed or given off by a hydrogen atom, given one or more principal quantum numbers, list the other possible quantum numbers. Given 2 of the following, determine the third using the de Broglie equation, mass, velocity, and/or wavelength. There are a number of terms that are associated with this chapter, including amplitude, wavelength, frequency, the electromagnetic spectrum, which includes the regions of gamma, X-ray, ultraviolet, also called UV, visible, infrared or IR, microwaves, and radio waves. Also, you should be able to define and distinguish between photoelectric effect, quantized, Bohr's model of the atom, what is meant by interference, both constructive and destructive, as well as what an interference pattern is, the term determinacy versus indeterminacy, the 4 principal quantum numbers, the principal shell, subshell, and what we mean when we say orbital. So why do we need to understand quantum mechanics to understand chemistry? Well, quantum mechanics is at the heart of our modern atomic theory. It explains why things bond together and in the particular geometrical arrangement that they do, which we will start to get into at the end of this series of lecture videos. The development of quantum mechanics actually comes from physics. According to classical physics, also known as Newtonian physics, light is a wave and energy is absorbed or released by an object in a continuous fashion. An interesting side note is that Newton actually did not believe that light was a wave. Instead, he subscribed to the idea that light came in tiny, what were called corpuscles or small particles. But in 1801, an English physicist named Thomas Young performed what is called the dual slit experiment, which we will get into in later videos in this section, which demonstrated that light behaved like a wave. But in the late 1800s and early 1900s, experimental results that contradicted many of the laws and theories of physics began to be observed. Some of these included the photoelectric effect, which is what led to Einstein winning the 1921 Nobel Prize. Others include black body radiation, as well as heat capacity. The last 2 we're not really going to get into in this series of lectures, but we will talk about the photoelectric effect and how that demonstrated that light, in fact, behaved as a particle, in addition to the experiments of Thomas Young, which we described previously, which showed that light behaves as a wave. So quantum mechanics actually brings together both the wave nature and the particle nature of light, and then was later expanded to describe a wave-like nature and particle-like nature to all forms of matter.